All right, so Ohm's law gave us a way to think about how current, voltage, and resistance work together in a nice simple circuit like an electric light bulb that's attached to a battery, but most circuits are a lot more complicated than that. And so we're going to start digging into more complex circuits, first of all, by thinking about what it means to have resistors in series and in parallel. So there are a couple of different ways that we'll see different resistors in the same circuit. A circuit can require that the current go through more than one resistor, as in this image up here. Um, like our flow of current is going to go through resistor 1, then 2, then 3, and back to the battery. And we say that these resistors are in series. Um, what we want to do when we have multiple resistors like this is we want to come up with what's called an equivalent resistance, right? So we're going to model this circuit as this circuit, okay? And then what is this RS that's going to be equivalent to going through all of these resistors? Well, the current here has to pass through all of these resistors. And so in this case, it's relatively simple to find that equivalent resistance. We're just going to sum those different resistances. Okay. And then we can use Ohm's law to find the current. So we take that equivalent resistance and put it into Ohm's law. We define that equivalent resistance as R1 plus R2 plus R3, and then we can solve for I here. Presumably we know the size of those resistors and the voltage. So what is the current through each resistor, right? We know what the total current is, but we want to know what it is through each resistor. Well, if we think about this physically, as you know, like our pipe, if we had a pipe that's going through here and it goes through one gate here and another gate here and another gate here, we know by the conservation of mass that that flow has to be the same all the way through, right? We can't have more water going through this gate than we would have going through this gate. Well, the same thing happens with current. Okay, we have a conservation of charge, which insists that if we have a certain amount of charge moving through here per unit time, which again is the definition of current, right? Charge per unit time. Then that same charge per unit time has to be moving through here, or we'd have a buildup of charge here or something, which wouldn't make any sense. So in series, the current has to be the same through all three resistors. And that can be important when we try and solve a problem too. So I1 through here is equal to I2 is equal to I3. The voltage, though, does not stay the same. And this is where resistors in series can get a little more complicated. Let's take our example here. Our overall voltage here, let's call it 12 volts. And we'll say we have a current of 0.1 amps. Okay, so that 0.1 amps is moving through all of these resistors. And that 12 volts of voltage is the difference between here and here. If resistor 1 is 40 ohms, then what we call the voltage drop, we can calculate using Ohm's law, right? So one version of Ohm's law is V, or change in V, equals I times R, right? This is just a rearrangement of Ohm's law. So we put in our current and our amp, and we get 4 volts. What does that mean? Well, it means that the difference between the voltage here and the voltage here is going to be 4 volts. So what's our voltage here? Well, it's 12 volts, which is our voltage here. And in a wire, again, we're assuming essentially no resistance. So the voltage here is going to be the same all along in here. It's going to drop by 4 volts. And so the voltage here in this section of the wire is going to be 8 volts, just 12 minus 4. If R2 is also 40 ohms, then we know that that drop is going to be 4 volts again, and so the voltage here is going to be 4 volts. So I can actually connect a wire from here to here and run some, you know, load on a 4-volt voltage difference. Okay, because I know that this, because of the way these resistors are set up, I know that the voltage here is going to be 8 and the voltage here is going to be 4. So let's think about this. You're getting tired of my metaphors, but think again about this as our water metaphor, right? If we think of each, let's call this a mill stream, right? And we're moving from 12 meters high to 0 meters high, and we want to turn some water wheels, and those are our resistors. Well, the stream is going to travel, level along here. It's going to stay at 12 meters or approximately 12 meters. And then it's got to do some work, right? So we need it to actually drop down um, to take the potential energy of that water at 12 meters and to turn it into motion on our water wheel. Okay, so it does that. It goes over the water wheel, it turns that water wheel, and in the process drops by 4 meters, right? Or in our electric, 4 volts. Okay. Then the second resistor is again a 40 ohm water wheel, if we can imagine such a thing. It drops another 4 volts. And then it drops another 4 volts here. And this is a really nice metaphor for this. It matches up very well. The height, again, is that voltage difference. The resistance is the load that is, some work is being done by that resistance. And the wires, there's very little drop in voltage because the resistance is very small. And then, of course, the current is how much water we have flowing through this object. You can see why a circuit like this is sometimes called a voltage divider, because you're dividing the circuit into different voltage levels, right? 12 volts here, 8 volts here, 4 volts here, and 0 volts here. And if I wanted to, like I said before, I could create a branch of this circuit that you'd have a full 4-volt difference there, or if I connected this to over here, I'd have an 8-volt difference. And so you can really, by changing that amount of resistance here, you can determine what the voltage is at different points in your circuit. So that's resistors in series. Resistors in parallel are also quite common. And you might have a circuit that's set up like this to power multiple devices. Why would you want to use this sort of circuit? Well, let's say we had a lamp, R1, R2, and R3 are all lamps. We want to run those all on the same voltage, okay? And we also want to be able to turn them off, right? I want to be able to turn off lamp 2 without turning off lamp 3. And I can do that in this circuit. If I shut down this circuit, it doesn't really affect what's happening here with R1 and R2. And that's different than in series. If I shut down one of those resistors in a series, it's going to shut down the whole circuit. So that's why we might use a parallel circuit like this. Now, voltage is very easy in a parallel circuit because the voltage is the same, right? This is a wire. And as long as it's a wire, there's no difference in voltage. That voltage all along here is 12 volts. And the voltage all along here is 0 volts. Okay, so the difference across here is the same as the difference across here, is the same as the difference across here, and is the same as the difference between the two terminals. Okay, so I can run all of these loads with the same 12 volts or whatever volts I have here. So V total is equal to V1, V2, V3. The current, however, is complicated, right? Because just like, use our stream metaphor, I have a certain amount of water flowing through here. Some of it's going to go through there, some through there, and some through there. I don't know intuitively how much is going to go through each one of these, and it depends upon our resistance here. So I total, that is the I right here and right here, is going to be the sum of this I, and that I. And that's our equation right there. Okay, so the resistance in a parallel circuit like this is also complicated because it's smaller than the smallest resistor. Now, that's weird, right? If I put resistors here, my overall resistance from here to here is going to be different because that's what we want to find here too as an equivalent resistance. Why is that? Because the current's going to take the easiest path it can, right? So if these were, let's say this is a 500 ohm resistor, this is a 500 ohm resistor, and this guy's 10 ohm resistor. Almost all of that's going to go through here because it's the easiest path, right? So if I made these big enough, right, my circuit would essentially just be this. And I could figure out what my current is just by using that 10 ohms. But if these aren't totally huge, if they're not much, much bigger than this, then I'm going to get that same circuit as if this was a 10 ohm circuit, plus some leakage through here, right? There's going to be some flow through there. So in other words, the overall resistance is going to be less than that 10 ohms, right? Because I'm also going to have some flow through there. And that means that my overall resistance is smaller than the smallest resistor. Again, we can think of this in terms of our stream or our pipe, right? That water is going to flow through the pipe that has the smallest resistance, say the biggest pipe, right? But some of it's going to go through the smaller pipes too, okay? And so having more pipes is going to mean there's going to be less resistance than if we just had the one big pipe. How do we calculate that overall resistance? Well, we use the inverses of the resistances. We sum the inverses and then we invert it, which is, not the funnest mathematical process, but not too